Hello everybody. Today we will be talking about I/O interrupts and I/O with DMA. I/O first, let's talk about I/O with interrupts. This method that is used to transfer information between internal storage and external I/O devices is known as the I/O interface. The CPU is interfaced using special communication links by the peripherals connected to any computer system. These communication links are used to resolve the differences between CPU and peripheral. There exist special hardware components between the CPU and peripherals to supervise and synchronize all the input and output transfers that are called interface units. The mode of transfer. Binary information that is received from an external device is usually stored in the memory unit. The information that is transferred from the CPU to the external device is originated from the memory unit. CPU merely processes the information, but the source and target is always the memory unit. Data transfer between the CPU and the I/O device may be done in different modes. Data transfer to and from the peripherals may be done in any of the three possible ways. The first one is programming I/O, the second one is interrupt-initiated I/O, and the third one is direct memory access DMA. Now, let's discuss interrupt I/O and DMA I/O. Interrupts. Temporary stopping of the current program routine to execute some higher priority I/O subroutine is called an interrupt. The interrupt mechanism in the CPU forces a branch out of the current program routine to one of several subroutines, depending upon which level of interrupt occurs. I/O operations are started as a result of the execution of a program instruction. Once started, the I/O device continues its operation at the same time that the job program is being executed. Eventually, the I/O operation reaches a point at which the program routine that is related to I/O operation must be executed. At that point, an interrupt is requested by the I/O device involved. The interrupt action results in a forced branch to the required subroutine. In addition to the needed to start an I/O operation, subroutines are required to transfer a data word between an I/O device and main storage for write or read operations, handle unusual or check conditions related to the I/O device, and handle the end of the I/O device operation. Interrupt-driven I/O is an alternative scheme dealing with I/O. Interrupt I/O is a way of controlling input-output activity whereby a peripheral or terminal that needs to make or receive a data transfer send signal. This will cause a program to interrupt to be set at a time appropriate to the priority level of the I/O interrupt. Relative to the total interrupt system, processors enter an interrupt service routine. The function of the routine will depend upon the system of interrupt levels and priorities that is implemented in the processor. The interrupt technique requires more complex hardware and software, but makes far more efficient use of computer time and capacities. The figure on the left shows the simple interrupt processing. For input, the device interrupts the CPU when new data has arrived and is ready to be retrieved by the system processor. The actual actions to perform depend on whether the device uses I/O ports or memory mapping. For output, the device delivers an interrupt either when it's ready to accept new data or to acknowledge a successful data transfer. Memory mapped and DMA capable devices usually generate interrupts to tell the system they are done with the buffer. Here, CPU works on its given tasks continuously when an input is available, such as when someone types a key on the keyboard, then the CPU is interrupted from its working to take care of the input data. The CPU can work continuously on a task without checking the input devices, allowing the devices themselves to interrupt it as necessary. Basic operations of interrupt. The first one is CPU issues read command. Then I/O module gets data from the peripheral whilst the CPU does other work. And I/O module interrupts CPU, CPU requests data, and last I/O module transfers the data. Interrupt processing. A device driver initiates an I/O request on behalf of a process. Device driver signals the I/O controller for the proper device, which initiates the requested I/O. The device signals the I/O controller that is ready to retrieve input. The output is complete or that an error has been generated. The CPU receives the interrupt signal on the interrupt request line and transfer control over the interrupt handler routine. The interrupt handler determines the cause of the interrupt, performs the necessary processing, and executes the return from interrupt instruction. The CPU returns to the execution state before the interrupt being signaled, and CPU continues processing until the cycle begins again. So, what are the advantages and disadvantages of interrupt-driven I/O? Advantages are it is fast and it is effective. The disadvantages are it can be tricky to write if using a low-level language. It can be tough to get various pieces to work well together, and it's usually done by the hardware manufacturer or operating system makers, such as Microsoft. Design issues. There are two main problems for interrupt I/O, which are the first one is there are multiple I/O modules. How should the processor determine device that issued the interrupt signal? And second one is how does the processor decide which module to process when multiple interrupts have occurred? There are four main ways to counter these problems, which are multiple interrupt lines, software poll, daisy chain, which is a hardware poll and is vectored, and bus arbitration, which is also vectored. These are known as the four general categories of techniques that are commonly used in I/O interrupt. First one is multiple interrupt lines. As the name suggests, we provide multiple interrupt lines between the processor and the I/O modules. This allows multiple modules to be handled at the same time. However, it's not practical to assign many bus lines and processor pins to interrupt lines. One of the reasons is that there might be more than one I/O module attached to a single line. This defeats the purpose of this technique. The three techniques of the latter are usually used together with this technique to rectify its problems. The other one is software poll. Whenever an interrupt is detected by the processor, it branches to an interrupt service routine which will poll each I/O module to determine the exact interrupting poll. The processor raises a poll which could be in the form of a command line. Consequently, the address of the respective I/O module which is interacted by the poll will be placed on the address line. The module will respond positively if it is responsible for setting the interrupt. On the other hand, every I/O module has an addressable status register. This register can be read by the processor to determine the interrupting module. After that, the processor is then branched to a specific device service routine. The downside to this technique is that it is time-consuming. Other one is daisy chain. This is actually a hardware poll. The interrupt acknowledges line is daisy chained to all the modules. Whenever there is an interrupt, the processor sends out an interrupt acknowledge, which will propagate throughout the series of I/O modules. This process will continue until it reaches a requesting module. The module will respond by placing a word on the data lines. The word is known as vector. This vector can either be the address of the module or a specific identifier. The process subsequently directs the module to its specific device service routine based on its vector. This technique is also known as the vectored interrupt. It completely removes the need for an interrupt service routine. Our last solution is bus arbitration. The last method, which also utilizes vectored interrupts, is bus arbitration. This method involves the I/O module gaining control over the bus before requesting for the interrupt. This is limited to only one module at a time. The processor sends an acknowledged signal whenever it detects an interrupt. The request module then places its vector on the data lines. However, when there are multiple interrupts at a single time, there will be a need to assign priorities. These four methods have their own way of assigning priorities. Multiple interrupt lines. The processor picks the interrupt lines with the highest priority. In software poll, the priority is determined by the order in which the modules are polled. In daisy chain, the priority is determined by the order in which the modules are polled, and in bus arbitration, it employs a priority scheme. Now, let's talk about I/O with DMA. The data transfers between a fast storage media such as magnetic disk and memory unit is limited by the speed of the CPU. Thus, we can allow the peripherals to directly communicate with each other using the memory buses, removing the intervention of the CPU. This type of data transfer technique is known as DMA or direct memory access. During DMA, the CPU is ideally and it has no control over the memory buses. The DMA controller takes over the buses to manage the transfer directly between the I/O devices and the memory unit. Different from programmed I/O and interrupt-driven I/O, direct memory access is a technique for transferring data within the main memory and external device without passing it through the CPU. DMA is a way to improve processor activity and I/O transfer rate by taking over the job of transferring data from the processor and letting the processor do other tasks. This technique overcomes the drawbacks of the other two I/O techniques, which are the time-consuming process when issuing a command for data transfer and tie up the processor in data transfer while the data processing is neglected. It is more efficient to use the DMA method when a large volume of data has to be transferred. For DMA to be implemented, the processor has to share its system bus with the DMA module. Therefore, the DMA module must use the bus only when the processor does not need it, or it must force the processor to suspend operation temporarily. The latter technique is more common to be used and it's referred to as cycle stealing. The figure shows an add-on DMA module cycles in an instruction cycle. Basic operation of DMA. When the processor wishes to read or send a block of data, it issues a command to the DMA module by sending some information to the DMA module. The information includes to read or to write command, sending through read and write control lines, number of words to be read or written, communicated on the data lines and stored in the data count register, starting location in memory to read from or write to, communicated on data lines and stored in the address register. Address of the I/O device involved communicated on the data lines. After the information is sent, the processor continues with other work. The DMA module then transfers the entire block of data directly to or from memory without going through the processor. When the transfer is complete, the DMA module sends an interrupt signal to the processor to inform that it has finished using the system bus. Here you can see another example of how DMA operation is done for input and output DMA. DMA mechanisms can be configured in a variety of ways, which are single bus, detached DMA, single bus with integrated DMA, and I/O bus. In the figure, we see CPU bus signals from DMA transfer. Bus request is used by the DMA controller to request the CPU to relinquish the control of the buses. Bus grant is activated by the CPU to inform the external DMA controller that the buses are in high impedance state and requesting DMA can take control of buses. Once DMA has taken control of the buses, it transfers the data. This transfer can take place in many ways. So first we'll start with single bus with detached DMA. All modules share the same system bus. The DMA module is acting as a surrogate processor, which uses programmed I/O to exchange data between memory and I/O module through the DMA module. This configuration is inexpensive but is inefficient. This is because each transfer of a word consumes 2 bus cycles, as seen below. Then we have single bus with integrated DMA. In this configuration, there is a path between the DMA module and one or more I/O module that does not include the system bus. The DMA logic can be a part of an I/O module or a separate module that controls one or more I/O modules. Therefore, the number of required bus cycles can be cut substantially. The system bus that the DMA module shares with the processor and memory is used by the DMA module only to exchange data with memory. The exchange of data between the DMA and I/O modules takes place of the system bus, and you can see it down in the figure. Last but not least, we have I/O buses. In this configuration, the concept is further improved from the previous configuration, which is single bus integrated DMA. I/O modules are connected to a DMA module using an I/O bus. This can reduce the number of I/O interfaces in the DMA module to one and provides for an easily expandable configuration. The system bus that the DMA module shares with the processor and memory is used by the DMA module only to exchange data with memory. The exchange of data between the DMA and I/O modules takes place of that system bus. Flows of using DMA by processor. It issues a command to the DMA module by sending necessary information to the DMA module. Processor does other work. DMA acquires control on the system and transfers data to and from within memory and external device. DMA sends a signal to the processor when a transfer is complete. System control returned to the processor. Advantages and disadvantages of DMA. Advantages are: it allows a peripheral device to read from write to memory without going through the CPU. It allows for faster processing since the processor can be working on something else while the peripheral can be populating memory. Disadvantages are: it requires a DMA controller to carry out the operation, which increases the cost of the system, and cache coherence problems. So let's look at comparison between interrupt-driven I/O and DMA. So interrupt-driven I/O means CPU. First we will look at interrupt-driven I/O, then we will continue with DMA. Interrupt-driven I/O means CPU issues commands to the I/O module, then proceeds with its normal work until interrupted by the I/O device on completion of its work. The problem with the programmed I/O is that the processor has to wait a long time for the input-output module of concern to be ready for either reception or transmission of more data. The processor, while waiting, must repeatedly interrogate the status of the input and output model. As a result, the level of performance of the entire system is degraded. An alternative approach for this is interrupt-driven input-output. The processor issues an input-output command to a module and then go on to do something other useful work. Then input-output module will then interrupt the processor to request service when it's ready to exchange data with the processor. The processor then executes the data transfer as before and then resumes its formula processing. Interrupt-driven input-output still consumes a lot of time because every data has to pass with the processor. Now we will look at DMA. Direct memory access (DMA) means CPU grants I/O module authority to read from or write to memory without involvement. The previous phase of I/O suffer from two inherent backwards. The one is the processor is tied up in the I/O transfer rate is limited by the speed with which the processor can test and service a device, and the other one is the processor is tied up in managing an I/O transfer. Several instructions must be executed for each I/O transfer. When large volumes of data are to be moved, a more efficient technique is required, which is direct memory access. The DMA function can be performed by a separate module on the system bus, or it can be incorporated into an I/O module. In either case, the technique works as follows. When the processor wishes to read or write a block of data, it issues a command to the DMA module by sending the following information. Whether a read or write is requested, the address of the I/O devices, starting location in memory to read from to write it, the number of words to be read or written. The processor then continues with other work. It has delegated this I/O operation to the DMA module, and that module will take care of it. The DMA module transfers the entire block of data, one word at a time, directly to or from memory, without going through the processor. When the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and at the end of every transfer. In programmed I/O, CPU takes care of whether the device is ready or not. Data may be lost. Whereas in interrupt-driven I/O, the device itself informs the CPU by generating an interrupt signal. If the data rate of the I/O is too fast, data may be lost. In this case, the CPU must be cut off, since the CPU is too slow. For the particular device, the initial state is too fast. It is meant to be allowed the device to put the data directly into the memory. This is called DMA. DMA controller will take over the task of CPU. CPU is a general purpose, but DMA controller is a specific purpose. A DMA module controls the exchange of data between main memory and an I/O module. The processor sends a request for the transfer of a block of data to the DMA module and is interrupted only after the entire block has been transferred. Here are the documents and slides I have used. Special thanks to Ujaz Taygun. These slides are based on his lectures. So thank you all for listening to me and have a nice day.